The ultimate goal of science, if we were to boil it down to the essentials, is to accurately describe and model reality in the most predictively powerful way possible. When we talk about the question of what is real, however, we're not simply looking at the question of, can my model make predictions about reality that agree with measurement, observation, and experiment? Instead, we're asking a more profound series of questions, looking at aspects like, is my model of reality self-consistent? Or does it have logical flaws? Does my model of reality maximize our predictive power about what we're going to measure? Or are there limitations to it that are surpassed by alternative models? Is my model of reality unique as far as its scope and explanatory power goes? Or are there other models just as good? And are all of the predictions of my model able to be tested and validated experimentally or observationally? Or are some of them hidden from our view in some fashion? Predictive power is an important aspect when it comes to understanding our reality, but many of our best current ideas started out as theories that were very disconnected from experiments and observations, but were later tested and sometimes validated directly. So where do we stand today on the big ideas of parallel universes and the multiverse? The notion of parallel universes goes all the way back to how we think about reality at a fundamental level in the first place, with a specific view towards the results of quantum physics experiments. Attempting to make sense of our counterintuitive quantum reality, including concepts like uncertainty, indeterminism, wave-particle duality, and predicting probabilistic, rather than certain, outcomes, is something that we've been struggling to do ever since we first began uncovering the bizarre, inherently quantum nature of our universe. And make no mistake about it, the rules that quantum mechanics plays by are not at all similar to the rules we're used to here in our everyday macroscopic experience. Perhaps the most famous experiment in all of quantum physics, and the one that best showcases the bizarre properties of our quantum reality, is the double slit experiment. Very simply, what you need is some sort of physical entity, like a wave or a particle, to propagate forward, in one direction through space, a barrier in that space that prevents the forward propagation of that entity, with two narrow, closely spaced slits in that barrier, enabling the entity to pass through the barrier in those two locations only, and then a screen on the opposite side of the barrier, displaying the pattern of whatever portion of that wave-like or particle-like entity arrived on that screen. That's the setup of the double slit experiment. Although it was initially performed by Christian Huygens back in the 1600s with water waves, it came to prominence around the turn of the 19th century when it was performed with light by Thomas Young. If light had behaved like particles, or corpuscles as Newton had theorized, then the screen would have been completely dark everywhere, with the exception of two bright bands that would appear, corresponding to each of the two slits through which light could have passed. On the other hand, if the light exhibited wave-like behavior, then what you'd expect would instead display alternating bands of light and dark, corresponding to regions where the light interfered constructively, additively, between the two slits, leading to bright bands, and regions where the light interfered destructively, subtractively or canceling out, between the two slits, leading to dark bands. Young's experiments, conducted in the late 1790s and early 1800s, decisively demonstrated the wave-like behavior of light under these conditions. Just as water waves propagating through two slits in a barrier would create two sources of circularly outward propagating waves that would interfere both constructively and destructively when they met, leading to a pattern of peaks and valleys in the water, light's wave-like nature ensured that it did the same. Further experiments conducted in the 1800s confirmed light's wave-like nature, and Maxwell's electromagnetism brought forth an understanding of light as the propagation of a sourceless, uncharged electromagnetic wave at the speed of light. But then things got weird, as in really, eerily weird. Max Planck demonstrated that the energy emitted in the form of light must be quantized, and therefore couldn't be made exclusively of continuous waves, but rather must be in the form of energy packets, where each packet possessed a specific finite energy. Albert Einstein demonstrated, through the photoelectric effect, that light could only ionize electrons if it had sufficiently short wavelength, irrespective of the light's intensity. In other words, it wasn't the total energy of a beam of light, but rather the energy of each individual packet, in which light was quantized. Packets that are today known as photons, that determined the properties and capabilities of that light. And then, In 1924, Louis de Broglie came along and recognized that things were even weirder than we had previously realized. It wasn't just light that exhibited this strange property of having particle-like behaviors under certain circumstances while exhibiting wave-like behaviors under others, but that everything including electrons, protons, atomic nuclei, and even whole atoms that exhibited this wave-particle duality. You could pass not just light but particles like electrons through a similarly set up double slit, and they would still generate that same wave-like pattern, showing clear evidence of interference. Then you could go and get clever and say, okay, I recognize that there's interference between the many electrons or photons in a beam, but what if I go and send them through single file, or one at a time? We performed those experiments and found that perhaps shockingly, the interference pattern still remains. By measuring particle after particle, a pattern begins to emerge, and it's the interference pattern, not the classical two piles that you might have expected. It's as though each individual quantum, like a photon or an electron, is somehow going through both slits at once, and interfering with itself. Perhaps you'll think, I know we'll catch each particle in the act, and measure which slit it goes through as it's passing through it. And you can do that, setting up a detector, like a gate for a photon or an induction loop for a charged particle like an electron, to measure which slit the quantum you're using is passing through. It works. The first particle passes through slit hash 1 and shows up on the screen. The second passes through slit hash 2, the third through slit hash 2, the fourth and fifth through slit hash 1, etc. But this time, there is no interference pattern on the screen. Instead, there are just two piles. It's as though the various quanta can tell whether they're being measured or not, and alter their behavior in response. You might be wondering what all of this has to do with parallel universes, and the answer comes from asking the question, if I can accurately detail all of the initial conditions of my physical system, including the experimental setup, and the positions and motions of every particle in it, then what will the result be? The rules of quantum physics, to the best of our understanding, don't give you absolute 100% certain answers. Instead, they only allow you to predict the probability of obtaining each and every one of the various outcomes. For a question like, where will this electron that I'm passing through a double slit land? We know how to calculate the spectrum of probabilities, but the only way to determine where the electron actually lands is to perform the experiment and make the key measurement for ourselves. All physicists agree on this much. This is simply how nature behaves. It may not be intuitive, and many of us may not find it satisfying, but that's the nature of our quantum reality. But then we do something that's only human, and ask, okay, but what's really happening with reality? And how does our notion that an objective, observer-independent reality exists square with these types of observations? And, as you might expect, it turns out there are a number of equivalent ways to interpret quantum physics. They include the Copenhagen interpretation, which posits that everything propagates like waves but interacts like particles, and that an interaction collapses the wave function, hidden variable theories, like the de Broglie-Bohm interpretation, which posits that there are deterministic hidden variables that we cannot see, access, or measure, but that if we could make 100% accurate predictions about the outcome of any experiment. The ensemble interpretation, which states that the quantum state doesn't represent one individual system, but only an infinite number of identically prepared systems, and the many worlds interpretation, which asserts that the wave function is real, there is no wave function collapse, and that all outcomes really do happen, but that we only live in one world, and so only measure one particular outcome with each experiment that we perform. Much attention has been given to these various interpretations as well as others, and trying to perform experiments that test their predictions against one another is an active area of research. In fact, quantum entanglement was the subject of 2022's recent Nobel Prize in Physics, which helped make quantum information systems the modern, robust scientific field it is today. But the question that most people, physicists, philosophers, physics students, and laypersons alike, want the answer to is simply, okay, but which interpretation of quantum mechanics is correct? Which one is right? And how do we know that the others are wrong? And to this question, for better or for worse, we have no answer, no consensus, and really no further clues than what I've presented here. Until, and unless, you can concoct an experimental test that can distinguish between these various interpretations and can measure reality to either be one way or another, all of these interpretations remain equally valid. We have just the one world that we can perform observations, measurements, and experiments in, and each time we only see one outcome. Meanwhile, when we calculate our predictions for what should happen, we can only arrive at a weighted probability distribution, not determine what the actual answer is going to be. So, are parallel universes real? Based on what we can say for certain about quantum physics, possibly, but there's no conclusive evidence supporting the notion. One big follow-up question we can ask is, okay, if parallel universes were real, where would they all live? The answer, according to standard quantum mechanics, is that they live in the same mathematical structure where the wave function lives, in a physical Hilbert space. That's all well and good, but our universe isn't well described as a physical Hilbert space, so that isn't a compelling argument. You could argue that if our universe is infinite, then because there are a finite number of possible configurations for the also finite number of particles that exist within our observable universe, then every configuration which arises in our universe must also exist elsewhere. In fact, if the universe is truly infinite, then that configuration must exist an infinite number of times elsewhere, and that would give these parallel universes somewhere physically real to live. Of course, we have no upper limit on how big the unobservable universe is. It could well be infinite. But finite is also an option. And if the universe is finite in extent, then it would stand to reason that parallel universes wouldn't be physically real. After all, if we're splitting off more parallel universes every time we have an interaction, make a measurement, or otherwise uniquely determine our quantum state, the number of parallel universes required to hold all of these outcomes swiftly approaches infinity. Now, it may be fun to speculate about parallel universes, but we have some information about where our own universe came from that seems to be especially relevant. We didn't just emerge from the hot Big Bang, but rather from a period known as cosmic inflation that preceded and set up the Big Bang. In inflation, the universe expands rapidly and relentlessly, doubling in size in all three dimensions, with each tiny fraction of a second that elapses, and then doubling and doubling again each time that same tiny fraction of a second goes by. This relentless doubling creates a veritable multiverse of independent hot Big Bangs and baby universes that emerge from it, including our own observable universe. The total number of universes spawned by inflation, just like the number of parallel universes required to hold all possible outcomes, also tends towards infinity as time marches onwards. But not all infinities are the same size. Some are bigger than others. Some infinities are bigger than others, and the infinity required for parallel universes to be physically real is a larger one than the infinity of universes created by cosmic inflation. That doesn't necessarily mean that parallel universes aren't physically real, but it tells us that, based on all that we know, there's no reason to assume that they are. They would be, if the universe itself were truly infinite in its physical extent, the inflationary period was past eternal, meaning that inflation lasted for an infinite duration before giving rise to our own observable universe. Or if we redefine physically real to include within the mathematical structure that we know of as a physical Hilbert space. Unfortunately for those of you who were hoping that I'd reach the conclusion that they were physically real, none of these count as the evidence we'd need to draw such a conclusion. In physics, there are different levels of what's speculative, where the least speculative extensions to what we know, like the existence of the inflationary multiverse, solely involve extending known, established physics into a realm that goes beyond what we know how to observe or measure, and the more speculative extensions involve untested assumptions that compel us to add new layers of complexity atop our already established reality. At this point in time, parallel universes are a fascinating idea and concept worth considering, but there's no evidence we can point to that suggests they're likely to be physically real in any way that impacts our observed reality in any way.